Imagine you need to design or build a chat app, a mobile game, or a stock trading app. All of these need real-time updates, but how do you actually do that? One of the best ways is to use WebSockets. In this video, we'll talk about what WebSockets are, how they compare to HTTP polling, long polling, and SSE, how you can design a WebSocket API for a mobile system design interview, and how to use them in iOS and Android. Let's dive in. Let's say we're implementing a chat application such as WhatsApp or Telegram. We need to implement sending and receiving messages, delivery checkmarks, and typing indicators. Most importantly, those features should work in real time, meaning we should see updates as fast as possible. Imagine you're chatting with a friend. You send a message and wait a few seconds before it shows up on their screen. That delay ruins the whole experience. That's exactly the kind of problem we're trying to solve. So how do we actually implement real-time communication between the mobile app and the server? Let's go through all the major approaches from the simplest to the most efficient. Your first thought might be to use push notifications for backend-initiated updates. They're easy to implement and don't require maintaining a persistent connection. Plus, they can even wake your app in the background. But here's the catch. They're not reliable and can be easily turned off in the phone settings. So push notifications might be used as an additional way to notify the user about new messages, but not the main route for data updates. Alright, the easiest brute force approach is HTTP polling. The app just makes repeated requests to the backend asking for updates. It's extremely simple to implement on the client. For our example, we would need to send an HTTP GET request to check for new messages every 5 seconds. Even if we get a response saying that there are no new messages, we still need to make another request 5 seconds later. Obviously, this approach would create an enormous load on the backend with all those redundant requests. I would say HTTP polling works better for larger time intervals, at least 1 minute or more, but not for chat apps. Alternatively, we can use the long polling approach, which is like an improved version of regular polling. How does it work? We make a GET request to the server for new messages, but instead of answering immediately, the server waits for new messages to arrive before sending the response. This technique is sometimes called a hanging GET. Of course, the server can't hold the connection forever, so it can't time out. In that case, we would need to send another request to the server to continue our long polling. This approach is definitely better because it gives us almost instant notifications, but it's more complex to implement, requires more server resources, and is complex to scale. The next strategy for real-time updates is SSE, or server-sent events. Usually people have a lot of confusion around it, so let's address it all. SSE is a protocol that enables us to push updates from the server to the client over a single HTTP connection. It's a unidirectional data flow, or a one-way data stream from the server to the client. It works like this. The client initiates an SSE by sending an initial GET request to the server, with the accept header set to text/event stream. The server replies with a confirmation and opens a persistent connection with the client. Afterwards, the server can send periodic updates to the client. If the connection drops, the app reconnects automatically and continues to receive the event stream from the backend. This method is much better than polling or long polling because it doesn't have the overhead of establishing and tearing down connections. Most importantly, if we don't have updates for the client, we don't have to send anything and waste network traffic. Also, the cool thing about SSE is that it works over the standard HTTP protocol, making it easier to integrate into our existing infrastructure. The downside of SSE is that it requires an open connection and, of course, it only supports one-way communication from the backend to the client. So for a chat app, you can use SSE for receiving messages and typing indicators from the server, but you would use regular HTTP POST requests to send messages. It's sort of like a hybrid approach. Cool, and now is a great time to introduce our top pick for chat application, which is WebSockets. Here's where things get really interesting. It is bidirectional or full duplex communication protocol. How does it work? It starts with an HTTP handshake. The client sends a special HTTP request with an upgrade WebSocket header. If the server agrees, they switch protocols from HTTP to the WebSocket protocol on the same underlying TCP connection. From that point on, it's no longer HTTP traffic. The WebSocket connection is established, and now both parties can send each other messages. Messages are sent as frames, small structured packets defined by the WebSockets protocol. The client and server can send them at any time without waiting for each other. You can send plain text or binary data through the WebSockets, which is really handy. Another benefit of WebSockets is that they reduce bandwidth consumption by maintaining a persistent connection. Now, let's talk about the downsides. The biggest problem is that WebSockets are difficult to set up on both the client and the backend. Also, they're difficult to scale on the backend and require specialized infrastructure. Your backend needs to keep track of thousands or even millions of open connections, which makes load balancing and horizontal scaling more complex than for HTTP requests. Additionally, WebSockets can impact battery life due to the persistent connection. The biggest hits are from aggressive retries or just forgetting to close the connection. On mobile, the most common problem is when a WebSocket disconnects because of a temporary network interruption. For example, losing a Wi-Fi signal for a few seconds. When this happens, the client needs a reconnection strategy. Typically, we need to detect that the socket has closed and reopen it automatically, using exponential backoff to avoid overwhelming the server with repeated reconnect attempts. On iOS, URLSessionWebSocketTask does not handle reconnects automatically, so you have to implement this logic yourself. The same applies for OkHttp on Android. So, to sum up, HTTP polling is simple but wasteful. Long polling is smarter but heavier. SSE is great for one-way server pushes, and WebSockets are the go-to option for bidirectional real-time communication, like chats or games. Alright, now that we know how WebSockets work, let's talk about how to actually design a WebSocket API, because that's a common question in mobile system design interviews. When we use regular HTTP, our endpoints usually look like this. But with WebSockets, it's a bit different. We use a different protocol prefix. So instead of HTTPS, we use WS for normal connections or WSS for secure ones. Similar to how HTTPS is the secure version of HTTP. When the connection is open, the client and server just send small JSON messages back and forth. So, how do we design those messages? Typically, every message we send through a WebSocket should include a type field that tells what kind of event it is, and a payload object that contains the actual data. Let's take a simple example, sending a chat message. Our client might send something like this: type payload, conversation ID, content message. Pretty straightforward. The server will parse this JSON and broadcast it to other users in the same chat. Since WebSockets are a low-level protocol, they don't provide guarantees about message ordering or delivery. For critical actions, you need to build that yourself. For things like chat, you might also include a timestamp or a sequence number in the payload to ensure messages are displayed in the correct order. Also, it would be a great idea to include in your design acknowledgements. When the server receives the message and stores it successfully, it can send back an acknowledgement event. That way, the client knows that the message was delivered and can update the UI. Here's what an acknowledgement message might look like. Type, message ACK, payload, client message ID, server message ID, and status delivered. So, by using this simple structure, message types, payloads, acknowledgements, and timestamps, you build a reliable system on top of WebSockets. It's flexible enough to add new features later without breaking what you already have. Now, let's talk about how to actually implement WebSockets on iOS or Android. We won't go deep into code here, but it's good to understand what tools each platform provides and how a basic setup looks like. Let's start with iOS. The easiest way to work with WebSockets on iOS is to use URLSessionWebSocketTask, which is part of URLSession. It's built in, pretty lightweight, and integrates well with your app's background sessions, authentication, and SSL. But one downside is that URLSessionWebSocketTask is quite low level. It doesn't handle automatic reconnections, message queuing, or background logic. So, in production apps, many teams prefer using open source libraries like Starscream because it provides a simpler API and all those features out of the box. Alright, let's take a look at basic example. When you want to connect to a WebSocket, you first create a task with your WebSocket URL, then send a message and start listening for responses. Then we need to listen for incoming messages. This is done recursively. Every time we receive a message, we call the same method again to keep listening. In a real app, you'd also want to handle disconnects and reconnects automatically, for example, when the user switches between Wi-Fi and cellular. You can implement that yourself or use a third-party library. Now, for Android, things are quite similar. The most common approach is to use the OkHttp library, which has built-in WebSocket support. It takes care of a lot of low-level details for you, like keeping the connection alive, handling ping-pong heartbeats, managing threading, and even automatically closing idle connections when the network changes. To summarize, URLSessionWebSocketTask or Starscream on iOS and OkHttp on Android are the standard choices to implement WebSockets. Now, here is a crucial mobile-specific tip. Handling background states. You can't keep a WebSocket open forever. When your app goes to the background, the OS will suspend it and drop the connection. So your strategy should be to gracefully close the socket when the app backgrounds, and then immediately re-establish it when the app comes back to the foreground. For true real-time updates while the app is in the background, you'll need to rely on push notifications. Another key thing is keeping the connection alive. WebSockets can stay open indefinitely, but if there is no traffic for a while, network layers or proxies might decide to close the connection. That's why you need to send ping frames periodically, usually every 30 seconds or so, and expand pong responses from the server. If the pong doesn't arrive in time, that means the connection is dead and you can't trigger a reconnect. On iOS, if you're using URLSessionWebSocketTask, you can schedule pings manually with something like a repeating timer. To wrap up, WebSockets is a bidirectional communication protocol that powers things like chat apps, real-time gaming, and live data updates. On iOS, you can use URLSessionWebSocketTask, and on Android, OkHttp library. Alright, thanks for watching, don't forget to like and subscribe, and I'll see you in the next one.